thank you everybody for being here for this new seminar, periodic seminar. Today we have the honor to, I have the honor to introduce Pedro Santos, and his talk is about the Internet of Things, which has become a hot topic lately, maybe in the real-time domain or in the wireless domain. Internet of Things has become a hot topic, as I said, in many application domains, automotive, avionics, or smart cities, for instance. A few words on Santos. He got his PhD in 2017 from FU. After his PhD, he spent 1 year of postdoc there, and he recently joined us for, I hope, many years, and I hope that you're going to have a lot of fun here.
Yeah, absolutely.
You will have around 30 minutes for the talk.
And it's possible that I extend it a little bit?
No problem. And you can have a talk interactive, so with questions in between or only at the end, at your own preference. So you have 30 minutes to entertain us on bridging vehicular and urban IoTs. Thanks.
Okay, thank you so much, Patrick. Hi everyone. So like Patrick was saying, I recently joined CISTER as a PhD researcher. I did my PhD at the field. I defended in 2017, and then I joined here. And I stayed there 1 year as a postdoc, and I very recently joined CISTER, like a few weeks ago. And so this talk is meant to be like a broad overview of the work that I've done in the past, so a little bit about my background. And hopefully, so it's not going to be very technical, it's more of an overview of the things that I've done. And hopefully some of this will catch your interest. If you want to discuss some of the results, some of the work in more detail, feel free to come to me. Also, if you find something that interests you, and perhaps you find it interesting, I'm more than open and willing to talk about it. Like Patrick is saying, I joined CISTER. I'm really excited to be here. I think it's a great opportunity. I think I'm really looking forward to do some nice work here. So let's move on to the talk. Like I was saying, this is going to be a talk about some of the work that I did in the past. And I would say that the work that I did in the last 5-6 years can be aligned into main areas that themselves are related with wireless communications, which is vehicular networking, okay, and also IoT for smart cities. So in the talk we'll be divided in these two parts. First I'll be talking about a little bit about vehicular networking, and then I'll be talking about IoT platforms, IoT solutions for smart cities, and also I'll be talking a little bit about the area where these two merge, okay, and where these two interact with each other. And also I should say that this is going to be a talk, most of the work that I'll be presenting is very experimental based, so I've been mostly on the roads, on the streets, doing some measurements, and so in most of the work, the results you'll see are mostly experimental. So let's start with the vehicular networking part. So I guess at this point, perhaps there's not much need to motivate this. The talk about vehicular-to-vehicular communications has been ongoing for a long time. There's even a standard that is more or less said to be the standard that will eventually be used for vehicular communications, which is the IEEE 802.11p, which is often also known as the SRC. And so there's a lot of already, for 10-20 years, there's already a large body of work on the communication between vehicles with infrastructure. And more recently, there's also been the trend to also integrate what we call vulnerable road users, which are road users that do not have the same levels of protection, like cyclists or pedestrians, to include them in the vehicular networking ecosystem. Okay, and so we are talking about pedestrians, We are talking, for example, about bicycles, and so, and also this element of communication between bicycles is also can be also seen as a scenario and a use case of vehicular networking. Okay, and so. But the way we integrate these vulnerable road users into the vehicular networking ecosystem is not very trivial, because the standard 11P was mostly designed for communication between vehicles. And so we don't see many commercial products being designed for vulnerable road users that use this standard. But we do see that people, cyclists and pedestrians do have their smartphones, and perhaps we might not use the 11P, but we can use perhaps the 11N or the Wi-Fi to achieve this vulnerable road user, this communication between VRUs and vehicles. So I guess this somehow motivates the work I'll be presenting. I'll start by discussing a little bit of work that I did on channel modeling and on propagation modeling. Then I'll talk about some work that I did in the past year. So this is perhaps the most recent work I'll be presenting about bicycle-to-X communications. And finally, some work that I did on routing. So let's start with the first part. This is somewhat old work, but I think it's interesting to mention it, and also shows a little bit about my background also in propagation modeling. So when we are doing channel modeling, we are trying to model the signal strength that a receiver receives from a wireless transmitter as a function of the distance, okay? And so when we are doing this kind of models we usually, when we are trying to do these models, we often, these models are useful to estimate RSSI in certain conditions. And often we obtain these models from actual measurements that we do on site. And so we call those empirical models, like, for example, long distance path loss model. And so we do the measurements, we take received signal strength at given distances from, in this case, the transmitter to a receiver. And then using that same data, we can extract or estimate the parameters of that model. In this case, the transmit power at, let's say, a reference distance, 1 meter, and also the decay of the power with respect to distance. And the important thing, and the relevant thing about empirical models is that these parameters can change depending on the setting where you are. These parameters might be different if you are in a rural area, if you are in an urban area, or if you are indoors, okay? And that's why these empirical models really require you to take the measurements in order to estimate the parameters of the model. The question that we asked in this first work was, in many vehicular models, in many measurement campaigns for estimating channels for vehicular scenarios, we use GPS to compute the distances between transmitter and receiver, okay? And GPS comes with an error, and our question is, okay, so exactly how is going to this uncertainty on my position going to affect the estimation of these parameters, okay? So we can talk about the true model, which is the one in which you use the actual distances. We can talk about a model that has some error associated because the distance that we get from the GPS itself also has some error, okay? And I can show you here the exact impact and consequence of having this error on GPS. So we did some measurements at known distances. We did some measurements of received signal strength. So the power strength received by a receiver at known distances from the transmitter. And you can see that when we use the GPS distances, we get one model. And when we use the true distances, we get a completely different model. And this is obviously biasing our model of that we will use to estimate the signal strength, okay? So we confirmed that indeed there's some bias going on. So we developed this small model for the GPS error, and in particular for the model for the error of the distances that we obtained from GPS position estimate, okay? And we observed that the end formula for the distance drawn from the GPS according to this model would follow a Rice distribution, which is like this one shown here. And each line corresponds to the distribution of the GPS, of the error of the distance for a known exact distance. Okay? And we looked at the data that we collected, and we did that somehow our data fitted the theoretical formulation that we created. So this was an interesting result, and so we went further and we did two contributions, which was to propose some guidelines in the sense that we recommend that you don't take measurements or that you don't use distances from GPS measurements at below when the true distance is below some threshold. And we were also able to develop a mechanism to try to retrieve the original, the true channel model parameters. Okay, and that comes from the fact that the RSSI samples are the same in both cases for both the wrong model, the erroneous model, and the true model. And so with our Monte Carlo method, in which we basically produce artificial sets of known distances, we distort them with our error model, and then we basically pair, and we produced RSSI samples using the erroneous parameter models that we then pair with the true distances. Okay, and then we are able to this is switched, and then we are able to estimate true parameters from this small mechanism. Indeed, because this is a Monte Carlo method, we have to do many iterations. Then we get the distribution of the parameters that we want to attain. That may not be exactly the same as the true ones, but what the important takeaway is that in the end we are able to somehow correct the wrong model, the erroneous model, into something that is closer to the true model. Okay. So this is the first element, a first contribution that I wanted to talk to you about. And so now let's move on to the second part, the propagation and the bicycle-to-bicycle networking. And actually this also is a propagation work in which we are also trying to estimate the received power strength via receiver, given a known transmit power, that notion that it will have, that the free space will include, but we also want to include the impact of the bicycle body on the signal itself. So let's assume we place an antenna somewhere on the bicycle, and you can already see that whether, depending on where you put it or the relative orientation of the bicycles, the bicycle body will have an impact on the electromagnetic signal that goes from a transmitter to a receiver. Okay, and this is a work that I did in the past year. This was in the context of a project with a company, and so this somehow motivates the reason why we're looking into bicycles, but also not only that, but also because there's a huge gap in terms of vehicular networking for bicycles. There are some works that look into propagation between scooters, but really for bicycles, there's been very little work. And because the bicycle body is so different from, for example, a car, there's some interesting challenges in this. When we talk about placing an antenna in a car, you usually think about placing the antenna on the rooftop, and that's it. You don't really think much more about it. That's often the approach that is used. But when we are talking about a bicycle, where to place an antenna and what's the impact, for example, of the material of the bicycle, those aspects can play an interesting role. Okay. So what we did is we selected a set of positions on the bicycle for the antenna. Okay. We also got 6 bicycles with 2 different materials. Some had the frame made of steel, and others had the frame made of aluminum. And we placed all of them in an anechoic chamber. Also, we made this in all of the bicycles. We made measurements for all the positions for all the bicycles in an anechoic chamber, so that we could get something called the radiation pattern. Okay, which is as I rotate the bicycle, is actually what's the impact of the body on the received signal. Okay. So in the case of the handlebar, if you think about it, you have the antenna in the middle of the handlebar. There's very little elements attenuating the signal as you rotate the bicycle. So you get almost an isotropic pattern when you have the antenna in the handlebar. But for example, if you put the antenna under the seat, it becomes very different. In this case, also let me have here this small help. So in this case, you have the receiver on the front at 0 degrees, and then the idea is that you start rotating the bicycle, and you record the signal at that angle. So, but in the case if you place the antenna under the seat, if you're communicating if you're transmitting towards the front, you'll see that there's a strong attenuation on the signal, basically because you have the seat. So if my receiver is over there, you'll have the seat and most of a big part of the bicycle body between the antenna and the receiver. So that's why you see this large decrease in the received signal strength when you have the antenna on the underseat. Same wise when you have the antenna on the back rack. And then these are slightly trickier positions because they're placed between the crankset and the cogset. And so when the antenna is actually facing the receiver, you have excellent reception. But then as you rotate and you have the bicycle body between you and between the antenna and the receiver, you start having this less optimal patterns, right? So they are much more reticulated, and so in some angles you'll have good transmission, but in others you don't have so good. And so we also did some simple experiments outdoor to see if this model would be of any help. Let's say if this characterization of the radiation patterns of the bicycles would improve our estimation of in the real world. So we had one bicycle standing on the middle, more or less in the middle of a football pitch, and the other bicycle going around the football pitch. And what we see here is a time series in red of the RSSI that we measured, and then in green our prediction with respect to what we were expecting to receive. And we see that if we don't account for the contribution of the radiation patterns, if we just look at the free space path loss, perhaps we would get a slightly better estimate of the measured value. But so this didn't really contribute a lot to make the case for the relevance of incorporating the radiation patterns. But still, we have some ideas that we can explore in terms of improving this. So this was the first part that I did on propagation. In the context of the same project, we also looked at some metrics on the upper layers, namely channel link. And so we also looked at throughput and PDR. And in an early stage of the work, we were trying to decide which technology to use. So we looked at 3 of them, and we did some initial experiments to see the throughput and the range that we would get with each one of those technologies. So we were talking about 15.4 Bluetooth and also Wi-Fi, but with different data rates. Okay, so using auto rate 1 megabit or 24 megabits. Okay, all this X scale. So the idea here is that we have a bicycle that is standing, and the other one is going back and forth, and that's what we see here as the bicycle, as a transmitting bicycle. On the X-axis, we have the transmitting bicycle approaching the standing bicycle, which is here in the middle, and then moving away, okay? And you can already see that there's considerable difference between the ranges, but also the throughputs, maximum throughputs that we measure in each one of these technologies. In 15.4, we didn't go to more than 50 kilobits, but we had a range of almost around 50 meters, 40 meters, as the bicycle was approaching and moving away. But on Bluetooth, we have somewhat better throughput. It goes to 1.5 megabits, but the range is comparably much smaller than, for example, the 15.4. As a general rule, we see that as we go higher on the data rates, the range tends to decrease a lot. In this case, we have looking at Wi-Fi at 1 megabit. This was really the technology that provided the most range. A couple of things that we observe is that there's some asymmetry regarding on the throughput that you measure as you approach the standing bicycle and then as you move away. Okay, so these curves are not exactly the same, and this is somewhat visible in other cases. Also, we observed that the auto rate that is used by Wi-Fi doesn't work so well because, let's say that it has a delay. It always tries, the auto rate algorithm is always trying to compute the best data rate for a given position, but because we are talking for a given channel condition, but because we are talking about moving terminals, it might happen that when the data rate is actually used, the condition for which it was computed is not, it has passed, let's say so. And now also, okay, so also some other work that we also did also at the link level is about what happens when we are looking to a bicycle to vehicle link, okay? And this also comes, an interesting aspect of this part of this work is that we did deploy a dedicated setup, Wi-Fi setup, for these measurements, but we also use the cars on hotspot, okay? So many cars nowadays have this hotspot which allows you to have Wi-Fi inside the car. And they usually have a cellular connection to communicate out to the internet, but the hotspot is providing Wi-Fi for the passengers, and there's little talk, and there's not so many works that explore the use of this in-car hotspot to communicate to users that are outside the car. Okay, and that's what we try to do. In this case, we see the radiation. We did some very coarse radiation patterns for our dedicated setup. So basically, a Wi-Fi antenna placed on the rear view mirror. But we also did for the in-car production system. Okay, and so these are quite different, and these radiation patterns mean that depending on the scenario, you might be at advantage or disadvantage using one or the other. And so we also tried this on a few real-world scenarios. There's this typical safety scenario of an intersection. We had the stopped car here, and the bicycle would approach and pass by. But there's a very particular scenario that I especially like, and that's very specific to cars and bicycles. That is when you have a stopped car that is stopped on the roadside parallelly, and you have a bicycle coming from behind. And so if the driver is not aware, he may open the door and there's a crash with the incoming bicycle, okay? So we did some measurements with these two scenarios, and in this case I'm showing the results of received signal strength only for this case. And we can already see that whether we are using our dedicated setup that is a bit further in the car, or if we use the production system that is a bit to the back of the car, we'll see that the received signal strength can differ significantly whether we are receiving the signal in this one or in this one, okay? And so this already complements these radiation patterns that none is better than the other, just that each one will operate better, will perform better in particular scenarios, okay? So let's move on to the second part, the IoT for smart cities, okay? And I'll try to cut it short, but again, I'll be talking about two urban sensing platforms that I was involved with, which were Port Living Lab and Urban Sense. And I think Professor Anna did a talk here some time ago, and she probably talked a little bit about this. And then I'll talk about that union that I was talking earlier on the beginning of the talk of the Venn diagram, that some use cases and some work that I did on where these vehicular backhauls really integrate and cooperate with these urban sensors that we might have in the city. Okay? So the context here is that we have, in a smart city, you'll have a number of sensors that can be in garbage bins, on some advertisement board, or some dedicated sensors. But then you will also have some backhauls, wireless backhauls, through which these sensors can send their data to the cloud. Okay, so assuming these guys don't have a cellular 3G connection, you can make use of either access points that already exist in the city, or you can use perhaps the access points that are now becoming common, for example, in vehicles. For example, in STCP, you have this Wi-Fi service that can be used not only by passengers, but also by these roadside elements to transmit their data. So I'll talk a little bit about that here. And finally, if we have the time, I can talk a little bit about an interesting work that also relates to this scenario that I was just talking, okay? So let me start by introducing the Port Living Lab, which was, so this was the outcome of FP7 project that we had here. I think what say it lasted between 2013 and 14. And the idea is to deploy IoT platforms in the city of Porto. And the IoT platforms that were deployed were mainly these three. BuzzNet, which were a set of onboard units that were installed in the buses. These were around 400 for the buses, 600 in total. And so this started with this FP7 project that was called Future Cities. And also the roadside units that are placed throughout all of the city. And this initial deployment eventually, it's this obvious onboard units that are actually providing the Wi-Fi on the buses, STCP buses. Okay. This deployment eventually led to the creation of a company called Venium. Their big selling point is that these onboard units not only have a 3G connection, but they also use the SRC communication, which is this vehicular standard. And the idea is that whenever you have, so you have the onboard, these access points, onboard units, providing internet to the passengers, and their connection to the internet can be via two ways. It can be the cellular, or can be between the onboard unit and the bus to this roadside units. So the point is that if you have a roadside unit near you, you can use this link to reach out to the internet instead of using the expensive 3G connection. And this is, I guess, I always believe this was a big selling point of Venium, because the idea is that you can you don't need to use the expensive 3G connection if you have these infrastructural nodes to which vehicles can connect. There was also Urban Sense, and this was the platform I was the most involved with, which was a set of 20 sensor nodes deployed in the city of Porto. I'll talk a little bit about more of that. And there was also a third platform, which is that target, the goal was to collect data from people's smartphone. And with this, we get data from the people, for example, GPS position. We also get some context information such as, for example, which Wi-Fi networks does my smartphone sees when I'm traveling from my home to my work. Okay, and so all of this three platform IoT, let's call it IoT platforms, smart city platforms, were deployed in Porto, and there we really got the chance to collect some interesting data and do some interesting analysis. We have here, for example, average speed of the buses. This is the origin destination matrices of the passengers from the Wi-Fi sessions of the passengers to the onboard access points of the buses. We also got to collect some temperature of from Urban Sense at different locations in the city. So this really gave us a much finer resolution in terms of measuring the temperature throughout the city than what we had before. And this, for example, is interesting. a case in which there was a week in August of 2015, I think, in which there was a lot of fires around Porto. And so what we did is that we looked at air quality metrics during that week and the weeks previous and after, and we really see that it was really noticeable, the impact of the fires on air quality during that week. Okay. And this finally also, I believe Professor Anna perhaps mentioned this, which is also using the app, that the Sense My City app that people install, we get to compute how much people take from their place to their work. If they work at Philp, we can learn about how long do they take to reach Philp. Or in this case, we can we would ask people to insert their happiness at the given location. So we could somehow do this happiness map, where people say where they're the most happy or not. Okay. So I'll move on to talk a little bit about the urban sense. I already mentioned briefly. So these were 20 sensor units that we call data collection units, that we equipped with ozone, NO3, carbon monoxide, particles, temperature, humidity, sensors, also wind speed and direction, and also rain gauge. Okay, the core of the DCUs would be this would be a Raspberry. And they would also have a Wi-Fi interface. Okay? There's also a noise sensor. And the way they could communicate was either via Wi-Fi to a nearby access point, or, as you'll see later, also they could transfer the data to the buses. Okay, I think there were 20, I guess most of them are out. There are left like 5 of them. So it's... perhaps you'll still get the chance to see one somewhere in Porto. And this was, it seems like it's not much, and we felt like this was going to be relatively simple to manage, but it turned out to be really hard to manage. Because there were a lot of factors that had to be factored in the operation of this several sensor units. So first of all, we developed some KPIs. We would have the uptime per sensor. So yeah, that's another thing, that each sensor would have its own behavior, and that itself added some complexity to the work. We would develop this data availability map. So per week of some month, for each location, we would see which data we had available for a particular sensor. When we also, in terms of operational time per site, we would have a ratio of uptime, but then we have 2 ratios of downtime, which is the known downtime and the unknown downtime. And the thing is, the known downtime is the one of which we know the causes, and the unknown downtime is the one of which we do not know the causes. And this is because, and this goes into some of the problems that we faced, is that, for example, we are dependent on the infrastructure of other third parties, okay? For communication and also for power supply. So when some of these DCUs went down, we were not really sure if it was the DCU that had went down, or if it was the power supply that had went down and that we didn't have that information, or if it was the communication that had went down. Yeah.
So how is the sensor box powered?
So most of these boxes would be installed on traffic lights or light poles, and the power supply would come from the pole itself. So this was done in participation with the municipality, and they were providing the power for the boxes.
Okay. Do you think about powered by energy harvesting or solar panels?
Not energy harvesting, but solar power. I'll talk a little bit about that later. And so there was this issue of being dependent on the infrastructure of others that we could not control. But we also had some problems from the fact this had been designed from the start to be a low-cost platform. And we went for Raspberry Pis, and one of the things that we saw is that the Raspberry Pi boots from the SD card, and SD cards are very volatile. So they are very fragile, and they can be corrupted very easily. So in the end, we had this guy working for 6 months just trying to figure out how to improve the SD cards. And so what had initially started by being a low-cost platform ended up being really expensive. Well, we had this one guy working full-time just to solve this problem. He tried all sorts of cards. He tried to minimize the use of the card. But in the end, this was really a problem in the sense they would get corrupted really easy. Even when we went to the sites, it was kind of a gamble. The Raspberry, the SD card could last 6 months or could last 1 week. It was always we were never really too sure about how long they were going to last. Okay, and then there was also wear from the elements. Let me show you some photos of this. So we had 2 DCUs placed near the sea, and they got corrupted very quickly by the salt. Okay, so this is the images from the time from those DCUs, and they became inoperable very shortly after we deployed them, like 1 or 2 months. The salt had completely corrupted them. And this is one of the cases in which we are dependent on a third party. We were using the Wi-Fi access points of a company called, not a company, but an institution called Porto Digital that offers a public Wi-Fi, free Wi-Fi service throughout all the city. And they had this access point somewhere here, but it was not tilted enough, so we were not getting enough connectivity on this DCU that was placed on this traffic pole near the Estádio de Dragão. And so we would keep asking them, please tilt the antenna a little bit so we can get connection, please, please, please. And they never ended up doing it, so we had to resort to a cellular connection on this place. And so, yeah, so it became really it was very challenging to keep this working. In a seamless and transparent way. We started by being a team of 6 to 7, but then the team started shrinking, and so it was hard to go to all these places. Constitutional coordination was also always tricky, so everyone felt they had the right to the data, but the university felt, no, we should sell the data, not give it. So there was some frictions and tensions because of managing this. And also, I think this is a major issue with this kind of platform, is that there's a lot of technical and logistic work that goes into it, but then it's really hard to publish. Okay. Yeah. Also on that, not energy harvesting, but we did try to make them solar powered. Okay, so we had this Erasmus Plus student here for 6 months. He was from renewable energies, and he really did try to find the best configuration for the size of the solar panels and the size of the battery that we needed to make the DC autonomous. Okay. It was really funny because he was from renewable energies. We didn't have such a strong background on that, so it kind of ended up being an interesting interaction. He ended up developing this simple greedy algorithm to try to find the best size for the power production capacity of the solar panels, but also the battery capacity. And this is the number of days that we will go with an empty battery, which is 0.05%, which is quite small, using these configurations that he eventually computed. But this is interesting, and this opened up some ideas. Is that are, if your sensor unit, if you can deal with not having data for some, let's say 1-2 hours per night, perhaps you can go for a smaller size setup and in that sense, you'll be spending less money. So, and there's this trade-off between spending too much money on making this stuff autonomous, or dealing and living with the fact that you won't have data for 1 or 2 hours in the night, which perhaps you can live with, and it will cost you less money. Okay. And now we go to the second part, which is where these two, the DCU and vehicular network interact. Okay. The first thing that we did was that in a DCU that we had in the main gauge, we had this Wi-Fi antenna, and so as buses would pass by, we would transfer the data, and we would measure how much data can we transfer. And this was done in August 2014, so this was prior to the commercial operation of the bus Wi-Fi service. And this meant that we could do some extensive measurements without hampering or interfering with the service. And indeed, we saw that in some days during the period of the measurements in which we were transferring the data to the buses that were passing by, in some days we were able to achieve 5 gigabytes of data, of data volume that we could transfer to the buses. And we also saw that when we plotted the transferred data per hour of the day, we could see a nice relationship with the number of scheduled pass-bys of the buses, but also with the ones that we actually ended up observing. So during the night, we see that the transfer data, but also the number of contacts, it's much smaller than during the day, and we also see some impact of the rush hours. Okay. Finally, and this. An interesting work that we did was to see, also in this line of estimating the I2V service, was the question whether, well, I know that there's a number of elements on a location that will tell me, that will affect the I2V service, namely the number of stops that the bus or the garbage disposal truck has to do, for example, caused by traffic lights, crosswalks, or if it's a garbage disposal truck by a given garbage bin, okay? And because we have the throughput that we measured, and we could relate it with the GPS location of the buses, okay, so in this case you have the data collection unit here that is communicating to the buses or to the garbage disposal trucks that are going through these roads. We know where the vehicles were stopped, and we know where we got the most throughput, and we know for how long they were there, okay? So when we compared, when we looked at 3 sites in the city of Porto, we broke down the data volume with respect to each one of these points of interest. We see that in the first case, a lot of the data transfers were happening at the traffic lights. But for example, in site C, we saw that a lot of the data transfers are actually happening near a garbage bin, because again, this study was done with a data set of the garbage disposal trucks. Also, there were some points of interest that we did not see coming, that we didn't assume, which, for example, in this case, which is 24 de Agosto, a lot of the data transfers happen with vehicles in the middle of the intersection. In the middle of the intersection, you cannot really relate it with a crosswalk or a traffic light or a garbage bin. It just happens that there's so much traffic in here that most of the connections end up also happening in the center of the intersection. Okay, so I'm close to wrapping up. Thank you for your patience. We also, so moving further on the protocol stack, we also did some work on networking, and we looked into some delay tolerant strategies in order to ferry the data from the DCUs to an onboard unit that later on goes to a roadside unit, and from the roadside unit you can forward it to a server. Okay, and so we developed we started by looking, and this was done in partnership with Venian. We started looking at some existing implementations, namely IBR.DTN, but they soon found out that this used too much energy. So they started building an in-house alternative. It's also important to notice that in this case they never ended up doing multi-op. So It transferred the data from the sensor unit to the onboard unit. And you could expect that the buses will also share this data between them, but in the end, the strategy was all about data milling. So the bus does not share the data it collected from the data from the DCUs. It just takes it and then drops it at the nearest roadside unit. And we did a proof of concept with this, and I think it would be funny also for you guys to get a little bit more feeling about this. That I show you a small short video that we did back then, which is not starting. So this was one of the DCUs, precisely the one in the middle, guys. And when buses pass by, the Wi-Fi, they would connect via Wi-Fi to the buses. The buses would take the data to a roadside unit, okay? And so we did a small proof of concept using the data, and then that eventually led to a demonstration that we showed in the conference. So in this case, we have the data collection unit, temperature sensor, and this is the actual onboard units that were deployed at the time on the bus. So we were actually using the hardware itself. So it's a very simple idea, is that just the DC will transfer the data to the onboard unit, and so this scooter is acting as a bus. And so as the bus approaches the roadside unit here, it delivers the data to a server. Okay, so very simple idea. Just showing the video for some more context. And finally, just to conclude, and this already starts leaving a little bit the realm of this interaction between the BuzzNet and the urban sense, but I also feel it's an interesting example, which relates to a user experience that people have been experiencing. So imagine that you have a smartphone, you go into the bus, you connect to the onboard Wi-Fi service, and you get the network memorized on your cell phone. And then you go outside, you are on the streets, you start using cellular, but then a bus passes by and your smartphone starts connecting to the onboard access point. And so this can disrupt your Wi-Fi experience, your internet experience outdoors. And our question was, well, can we prevent this? And we don't want a solution on the user side because it will be too cumbersome for people to have to install an application or have to forbid some disconnection to this particular SSID. So we wanted to do a solution that would be on the onboard access point. And what we had available was, for one, the position and speed of the bus, but we also had the RSSI of the received from the user's smartphones, okay? So the access point would collect the RSSI that the smartphones of the users would be transmitting, right? And so we went about it in a very data-driven way, and then we ended up developing a classifier for this. So we collected the data of the GPS locations and speed and of the RSSI of the user devices at the onboard access points for a week. And then we trained a classifier to tell us what were the features that were the most important, and to classify whether the user was inside or outside the bus. And so it turned out we developed the decision tree classifier, and it turned out that the most important features were not actually RSSI as we expected, but actually the bus speed, and eventually the speed right 10 seconds before the connection. Okay, and we integrated this in a broader mechanism that we deployed on the onboard units. That would make the decision whether the user was inside or outside the bus, and then, depending on the result, it would either allow or deny the connection. So people that were outside, they would be denied the connection. If you were inside, you're allowed to connect to the Wi-Fi service. And then just to test this solution, we deployed the classifier on an onboard IP that we placed on a private car, and we went for some trips around Porto. And in this case, the ground truth was easy. Everyone was outside, and the classifier, well, it didn't work so well. It was able to identify that people were outside in only 40% of the cases, but still, this is not accounting for also the potential classification of people that would be actually inside the vehicle. Okay, so that's it. I won't take you any more time. And thank you for your attention.
So yes, we have room for a few questions.
Yeah.
Quick one. So I was actually waiting to see when you would make this bridge within the vehicular communication and IoT.
Yeah.
So fortunately, I saw it later on, and I realized that most of this bridge was done, at least from what I could understand, while you were trying to optimize the placement of roadside units and taking into consideration your traffic conditions and where vehicles were moving, where we're stopping for the most time, for longer periods, right? So, and this is okay, of course, but to make this bridge more bi-directional, I guess a good challenge for the future could be to think about how you could use this data from the RSUs and use it to actually improve traffic.
Yeah. That's true. That's a good
Do you
idea.
have some ideas on that?
Yeah, well, it was a pity, and I really regret that earlier on in the project, there wasn't a decision to make some kind of sensors to include some sensors of the traffic. And I completely agree with you, because it's a very important urban process, which is traffic. But unfortunately, the Urban Sense platform didn't work with it. But there's some work that we got, but this was later on, perhaps after the project, that would try to estimate traffic. So we're talking about the vehicular traffic, right?
Yeah.
That would try to estimate the traffic from the BuzzNet GPS, from the GPS traces of the buses. And it's not so, it's a bit tricky because the buses are only a subset of all the vehicles in the city, right? So we're trying to estimate whether there's congestion or a lot of traffic on a particular road, but you only have a few samples here and there from the buses. So we're trying to extrapolate from these GPS traces of the buses whether there's a lot of traffic or not on this particular road. So that's one way to go about it, which is to take the GPS traces of the BuzzNet. In terms of the urban sense, I agree with you that there's a case of a missing opportunity. There was, however, an interesting component of the urban sense project, which was people counting. So not only we have this sensors that I talked about, we also would have cameras. And the idea was to count how many people are within the angle of the camera. And I would assume that could be extended also to vehicles. And there was an interesting worry about making sure that the collected data was anonymized. So we wanted to do, on the camera itself, we wanted to process the collected video stream and anonymize it in an easy way, in a way that we just needed a number of people in there. We didn't want to know who was there. But that part, for some reason, never went through. It was deployed, and actually we still find, besides nearby some of these DCUs, you'll still find a smaller box, which is a camera that was deployed also within the scope of the project. But that part really never took off. It's good. Okay. So, but I agree. Yeah, there's the other part of the cycle where you feedback. But again, it's you have to face an important challenge, which is this institutional coordination and institutional open. The institutions have to be open-minded to take this data and use it. And unfortunately, there is no feedback being fed back to the city, to the municipality from the data that we collected during the Future Cities project.
But they're doing something with the data, no? I mean, they did
Yeah,
something
yeah.
with the data.
We did. I mean, the municipality itself, or as we, as a team of the project, we tried to publish as much as. Actually, our problem was getting to process all the data that we collected. But we also acknowledge that there's a lot of gaps in the data. I show you the data availability maps, and you see that there's a lot of locations that don't have data. But that really is something that we have to live in, because it always happens when you're working with sensor networks. With sensor nodes, you will always lose some data somewhere along the way. So we did try to process as much as possible from the data sets we collect, and there's still a lot of data to process. Perhaps one of the issues is that we don't have the manpower to take care of all the data. Or we didn't have back then. Let's put it that way. Yeah, sure.
Regarding your last problem, so that the accuracy of your classification to identify the people outside or in the bus.
Yeah.
So I think instead of using RSSI, why not use CSI? Because CSI is more accurate for localization.
Yeah, that's a good point. We didn't look into CSI. We were just, our initial intuition about the RSSI was just that if you're close enough, you could have some kind of estimate whether you're inside or outside. But I think this, and perhaps that's something we didn't explore. There had to be like this temporal dimension to it, which is, well, if I have my RSSI increasing or decreasing, and probably not inside.
The RSSI can be affected by multipass,
Yeah. And also, if you're going into the bus and you're going to the back of the bus, your RSSI is dropping. But it's hard to tell whether you're just going to the back of the bus or if you're outside and the bus is going nowhere. So, but that's something we didn't explore actually.
Because I had experience before, so at that time we tried to identify students are in the classroom or outside the classroom.
Yeah.
So we also use RSSI, but the performance is really bad.
Yeah.
So I mentioned
And actually, that was that's what we concluded from the when we trained the classifier, is that the RSSI wasn't really playing a role. It was mostly about the bus speed that ended up being the most interesting predictor for whether the person was inside or outside.
So a quick, more technical question. There were a lot of different works, so I'm still trying to digest everything. But in that work regarding the bicycles and bicycle-to-bicycle communications, those performance measurements you made using RSSI and picking up on this question there, were made with a guy on top of a bicycle or with just the frame?
So I didn't show the results with the guy on top of the bus.
Yeah, because my intuition tells me that probably it will be
so he
used
bikes
for-
a lot. No question about it. No, I just showed the ones without. We were focusing on the bicycle. Because in the early stage, we were considering the contribution of the person to be, perhaps, we could add it in after we had the estimation of the bicycle itself. But I agree, but we then ended up doing measurements with the person inside, with the person riding the bicycle, and just for a smaller subset of positions actually. We use those initial measurements to say, okay, we have 6 potential positions, let's narrow it down from 3 to 3, and then we just do experiments. Because the other thing is that the measurements of the person cannot be done in the chamber. The stand wouldn't be able to support the bicycle and the person. So they had to be done outside. And we actually did them in Faber. We had to do them there. So the resolution that we got is also lower. We don't have 5-degree resolution, we have 10-degree resolution. And I didn't show those results. But also the validation that we try to do, we try to minimize the impact of the person. So that this wouldn't be much of a factor. But yeah, we also looked into the impact of the person.
And when you make those measurements with the GPS model in your first work here,
Yeah.
I'm assuming that that model is very much tightly connected to the GPS you're using. Right.
The model itself?
Yes.
The model is generic, right? If you tell me if I use a better quality GPS, of course.
Because the error of that GPS.
Yeah, of course. Exactly. And that really shows, and I can tell you where you see that. Because, for example, in the guideline that we propose, not the guideline, but actually, yeah. So this model that we create, and then that we use, for example, here in this case, when we do this guideline, this is dependent on the standard deviation of the error of the GPS, and this is something that is given to you on the data sheet. So if you have a small error, if the GPS will give you high accuracy, so this limit, let's call it this boundary, will shrink if you have a bad GPS. So it's really dependent on the device, like you were saying. So that's a good point.
Okay, let's thank the speaker once more.